heard of it?
Yep, it's on.
So it's on. Okay, so the kinetic theory of matter tells us that an explanation for why these things affect. So Dr. Weil likes the analogy of your students in a room, blindfolded, randomly moving, right? So you're walking around. Let's say we have blindfolded you and you're walking around. If you were like the control test tube, then you would be walking around blindfolded at a normal pace, right? Randomly walking. And if you guys were walking around here in this classroom randomly blindfolded at a normal pace, would you be likely to collide with somebody eventually?
Yes.
How forceful would those collisions be?
Not very strong.
Not very strong. But think, when you're a particle, you don't have a brain, so you're not being cautious, you're just moving at a normal speed. You would be likely to collide with the walls and each other at a reasonable rate. So collisions would be averagely likely, right? So then if we consider the less concentrated situation, what would that be like for a pack of students that are blindfolded and walking around at a normal pace?
Like half of us are moving around.
Okay, so either we'd throw half of you out into the hall, or
Put us on a smaller room.
to more concentrate you, we could get a smaller room. We'd all walk around in the janitor's closet. Would you be more likely to collide with each other?
Yes.
Yes. Would your collisions be more forceful? No, because you're moving at the same rate. What if I put you all in the gym instead of this room?
It'd be more forceful, but they would be more forceful because
All the boys would instantly start running when they're put into that environment? No. No. So you have to keep
Even
moving at the
blindfolded.
same rate because we haven't changed your temperature. So we'd just put you in the gym and you would have more space, so you'd be less likely to collide, but your collisions would be equally forceful as anywhere else. So reactions would be more or less likely in the gym. Less likely. And reactions would be more or less likely in the janitor's closet. More likely.
we should try that sometime.
Yeah, this is a lab I'm not really willing to do. And it wouldn't work because you all have brains and you would be cautious or careless depending on your natural tendency. This class is probably more considerate, but I have certainly had active classes that I would be afraid to do this with. Let's see, where are we? So concentration, definitely, you can see how that would be affected. How about surface area? What if you guys walked around at the same rate, but you walked around like this?
And we had a giant blanket and we just kind of like a sail. And
Yeah. Would you be more or less likely to collide?
Well, we'd be more or less more
More.
likely to trip if you have a giant blanket.
Right, and that could make your collision harder, but for a particle it wouldn't. You would be more likely to collide if you had more surface area, right? Let's see, stirring, I guess if we got in a pool, somebody turned on the jets, would we be more likely to collide? And this is where the analogy breaks down a little bit, because it does seem like you would have more energetic collisions in that situation, but as far as particles are going, you're really not raising the temperature, so that's really not the case. And that's a place that it's really hard to observe. So temperature.
We're all moving at the same, like in a pool, we're
Mhm.
all moving at the same rate. Shouldn't we not collide then? Like, you know how you get in the swimming pool and you do like a whirlpool?
Yes.
We're all moving at the same rate and then if each other.
Yeah, the pool
I mean, I know
It-
it's
It
just far.
But
depends.
it's
If there
stirring
is
would
something
randomize.
then you don't move as fast.
Yeah, every particle is different, and not every particle that is aqueous, say, has the same kinetic energy as every other particle in there, right? I mean, like, there are slow-moving liquid or aqueous particles and faster-moving. There's a lot more randomness in a solution than there is in that. I mean, chemicals are more complicated than you might necessarily notice at first. And temperature, here's the one that causes the bigger factor, right? So for a hot temperature, you guys would be here in this room blindfolded but running. Would you be more likely to collide?
Yes.
Would you be more likely to have more energetic collisions?
Yes.
Yes.
Yeah. So how about if you guys like moved very, very slowly, more likely to collide, very less likely to collide, and more energetic collisions, much less energetic collisions. Okay, so that's kind of thinking through the kinetic theory of matter to explain how these factors affect rate. So your two questions that you're going to write your little paragraphs about, and they can be handwritten or typed, either way. Use the kinetic theory of matter to explain the effects of temperature, concentration, surface area, and stirring on rate. So my suggestion would be...
These questions somewhere?
They're on the lab help sheet.
Okay.
So my suggestion would be you're going to want to write something about your prediction, something about your observations, and then perhaps a discussion of why we're baffled about concentration. I just don't understand how that happened.
Maybe we broke physics.
Huh?
Maybe we broke physics.
We broke the law. We definitely broke the law. I mean, I'm going to do it again if we have time with a much more
Is it a new
diverse-
bottle of
No, it's a
or
really
was it-
old bottle.
And I was recorded first, maybe. I don't know why that would make a difference, but
Yeah, you never
whatever
know.
would make a difference.
I mean, a chunk
could
of
be
like
more
dried up stuff could have
something,
fallen
yeah,
in or
on top of
something.
it, yeah.
But I've used that bottle 4 times, and I've never had anything remotely like that happen. And I can explain at least the crushed one because I think it kind of piled up and laid on the top of it.
Was it the less concentrated or the controlled?
The less concentrated that was the crazy one. It just reacted very quickly, even though it was less concentrated. And it ended up being number 2.
I think it might be something in the water.
Town Creek water.
But then why would it only
yeah,
be affected
yeah.
at room temperature and not boiled or cold?
Well, because we didn't put water into the reaction.
Oh, that's right.
In
Maybe
anything
then the
except
water
that
was
one.
warmer. Maybe it
That
wasn't
could
room
be.
temperature water.
Or the
Yes.
water wasn't very well mixed with the...
That looked pretty well mixed, but it could be. I don't know. I'm stumped.
We should try again.
Yeah, we are. If we have time, we'll try it again. And then the second thing, so definitely write about your prediction, about what happened, about your thoughts on how all 4 of those factors are able to affect rate. And then in the experiment, which of the factors seem to have the greatest effect on rate? So what would you say there? Temperature. Temperature seemed to have the greatest effect on rate. And which one seemed to have the least effect on rate?
The cold, or the least effect. Well, it was the, in
was
this
sad.
case, it was the crush.
I would say
It
the
was
crushed in
surface
this
area,
case.
but
But that could be some error. It seems like stirring and crushing are, well, I don't know, crush is usually very fast, and for you guys it was very slow.
well, when you say like which one was the most useful, which one helped the most, which one didn't help the most, they're both temperature. Just depending on what the temperature
Well, but
was.
it had a big effect on rate. It just made it
Oh.
slow.
So
So
it was which one was the most effective, whether it was a
usually,
fast or slow effect.
yeah, I mean, usually it would be either crushed or stirred. So take your pick and write why you think so. And then there's another experiment that we're about to do after we get through the lecture and stuff, and you'll have another paragraph or so added on to the end of this.
So you don't need to do like a separate.
No, you can put them right on one paper and just turn them in. And it's just a discussion paragraph. It's not like a whole lab report. So, did you get a good shot of the board, Jen? Just in case, we'll zoom in. Oh, you're zoomed in. All right. So there was some tablet left in some of those. And I can't get a good shot of the board because you are zoomed in. So I guess we can see it. All right, we're going to erase, and then we'll talk about the rate equation. So to calculate rate for you guys, you're going to use yes. All right, so if you have more than 2 reactants, you could have C to the Z, or however many reactants you have, you can include more than that, more than just the 2 in the rate equation. But that's just kind of an example of the rate equation. So rate is equal to a constant times the concentration, brackets mean concentration, of a reactant raised to a power times the concentration of another reactant raised to power, and you could keep going there if you have more reactants. And K is called the rate constant, and R, of course, is the rate. One fun thing that you might find is that units can vary depending on the overall order of reaction. So you have to figure all that out by essentially performing experiments where you hold the concentration of one reactant, or all but one reactant, constant, and vary the concentration of another one. Collect data, then hold the other one constant, vary the other one, measure the rate. And then once you've collected some data, you can calculate the rate constant. So that is more obvious when you do some problems. So let's look at review questions and then practice problems, I think. I have those guys. We did 4 review questions, maybe?
I could only do 3.
You could only do 3, that's fine.
I may not have read far enough, but I thought I read far enough.
That's
I
fine.
can only do 3 of the practice
Yeah.
problems, but I did 4 review questions.
Okay.
Oh yeah, never mind. I got 4 review questions. It was practice problems.
Okay. We'll get the ballpark, and then we might look a little further, and I'll probably lecture a little further if we do one more experiment, because you guys will have some microchems when you get back from break. And we won't have time. We might not have time today. All right, so number 1, we'll start with Micah, says, if 2 molecules want to react together to form new chemicals, what is the first thing that must happen?
Well, they must obviously collide in order to get so electrons so you have the chance to do it.
So they have to collide so their valence electrons can interact. And not every collision will bring a reaction, but they must collide. Number 2, Aaron says, a chemist runs a reaction at a low temperature and runs it again at a high temperature. Which one would you say was likely to be faster?
The one at a higher temperature.
Higher temperature. And we've clearly seen why that is. Liam, explain in your own words why the rate of chemical reaction increases with increasing reactant concentration.
So if it's more concentrated, there's more moles per liter. So more moles per liter, there's more chance of collisions instead of fewer moles.
Right, increasing concentration increases the chance that a collision will happen. Grace. A chemistry book lists the rate constants for 2 different reactions. The first one is 0.12, I don't know, that looks like a hertz to me after teaching physics, but 1 over second. And the other one is 34.5, 1 over molar per second. Even though the rate equations for these are not given, and a student says that the overall order of the reactions must be different. The student also says the second reaction is faster than the first. So why can you make those assumptions?
Because the rate constants depend on the order of the reaction, and so when we have units that are different, then the reactions are different, and the order is different.
Okay, so units being different tells you have different overall order, definitely.
What's the order of the reaction?
So here, there's a test question that's far too easy, and it's toward the end of the test, I think. And I had like an overwhelming majority miss it last year, like maybe 10 out of 12. And I've never had that happen before, but now I'm alert to this question. So the overall order of reaction is this exponent plus this exponent plus any other if you have multiple reactants. I don't think he ever gives you more than 2 reactants, but some chemical equations will have 3 or 4 or whatever reactants, and you'll just have, so you just literally add up the exponents, and that's the overall order of reaction. So if I say this reaction is first order with respect to this reactant, and it's third order with respect to this reactant. The overall order would be 1 plus 3 is 4. It's like, it's too easy to be at the end of a test, basically. But when your overall order changes, your units for that rate constant are going to change. So you can't just assume, like when I say, I give you a big problem about velocity, you're looking for the velocity, you can pretty well bet you're going to end with this kind of unit, right? And so people get sloppy not keeping their units throughout a problem. With rate constants, you can't do that because you don't know what your unit's going to be in the end unless you keep track of your units. So yeah, if you have different units to a rate constant, that's fine. It just shows that they have a different overall order of reaction. Now, Grace, tell us again how they could figure out which reaction was faster.
So the rate constant is based on the equation, and if you have like a rate constant that is larger than the other one, then you'll know that it's faster.
Right. So you just ignore the units and look at the magnitude. The first one is 0.12 and the second one is 34.5. The one that has literally the bigger magnitude, the bigger number, 34 as opposed to 0.12, is going to be faster. Faster the reaction, the bigger. So like with our test tubes, we could say the magnitude of the constant for the hot one is bigger than any of the others because it went faster. We might not be able to predict without looking at the chemical equation and running more tests what the overall order of reaction is, but we could definitely predict the magnitude of the number of the rate constant because the faster the bigger. And we didn't do 5, did we? We might talk about 5 before the end of the data. Is that still review questions? No. What is that? I don't know what that is. Crazy. Okay. Let's look at number 1 on the practice problem. So, Kristen, milk sours because of a chemical reaction that takes place between some of the chemicals in the milk. Why would a carton of milk spoil faster on the countertop than in the fridge?
The milk that's not in the fridge has a higher temperature, and higher temperatures and faster reaction rates.
Yep, higher temperature, faster rate, faster spoiling. Aim at not me.
Can you zoom in so it's just like the wall?
Eyeball will answer the next question.
Hi, Kristen.
Oh dear. Austin, Jolene, hope you're entertained. So, number 2 says a chemist does a reaction rate analysis on the following. And you have a whole chart and everything. And I am going to put up at least the first chart on the board just to make sure we're all on the same page here. So, what's NO, Jenny?
Are we ready? Do you want me to write?
I want you to tell me what NO is. Name it. Covalent or ionic.
Oh, darn it. I don't remember.
Yes, you do.
No.
You know.
I don't.
Yes, you
I
do.
don't remember.
Kristen.
It's covalent.
It's covalent, so you name it with prefixes. So what's it called?
I don't know. And I think you're just torturing me because you know I don't know these things.
I totally think you know this.
Oh.
Kristen.
An easy one. Nitrogen monoxide.
And then this. What's this one called? Come on.
I don't know. It's oxygen.
What is it?
It's oxygen.
Oxygen is elemental form. And what's this one? This is nitrogen monoxide. This is
Nitrogen dioxide.
okay. So we've got our reaction here, and they give us this beta chart, which I should have been writing this whole time. So they have trial concentration of not carbon monoxide, in molarity, concentration of oxygen, and molarity, and rate. And it gives you units of molarity per second. And 1, 2, 3, and then a practice line drawing. Right. So just to make sure we all really understand how to use our charts, because this is very important skill in this. I'm going to fill in. I'm going to change the color for my old eyes at least. Okay, so now we've got this chart. What are we going to make of this? So the problem wants us to do what? What is the rate equation? So what do you need to know to write a successful rate equation? What do we have to figure out?
To figure out the K.
Have to figure out K. And what else?
Well, I think you have to figure out X and Y.
Okay, X and Y. We need to know these exponents. So we've got three goals here, K, X, and Y. So how do we figure out X and Y first? So if I were to know the order of reaction with respect to nitrogen monoxide, which would essentially be X, right? Then I need to look at a situation where my rate or my concentration is constant for the other reactant, where I'm only changing the nitrogen monoxide. So between the first and the second trial, oxygen is constant. Then we can just look at the change in nitrogen monoxide. So what is the factor of change in nitrogen monoxide?
2.
Okay, so from here to here it doubles in concentration. So what happens to the rate when that doubles but this one stays the same?
I think it quadruple.
Okay,
Is
so
that what it's
quadruple.
called?
So in here, I look, this is constant. This doubles. And this
Oh, yeah.
quadruples.
This one, when I did it, I tried to do it with the second line, and I got the wrong answer, so I did it with the first and the third, and I got the right answer, but the second line didn't work for me.
Right, you have to look for a place where this one is constant
I mean-
and this one changes.
I mean,
and
when I
that could be
did-
different for different charts.
I mean, when I did all the math, like once I already had all the
Oh, like when you were looking for K.
looking for K, yeah. The first and the third was one
Let's
answer.
do it
the
that
second
way
was-
then.
Well, wouldn't it be when you have the same size of something reacting in a larger, I guess, gas, a larger amount of gas? Wouldn't it be able to react faster than reacting the same amount in a smaller amount of gas?
Okay, so theoretically, once you figure out the order of reaction and you're going for K, you should be able to plug in any of the three trials and get the right answer.
How does that happen? Because you've got like
We'll look
wrong
at it.
measurement.
I haven't done it for all three ever. I just usually do the first one because that's what most students do. But if you found one that doesn't work, let's try it together. So I need a color that will let me mark the other one. So Saul, here you take over, since this problem will go on forever, at least if I drag it out. So where is a place where we can hold this constant and vary this one? Which two trials do we want to compare where this is constant?
The first and the third.
First and third. So this is constant. So what happens between the first and third trial here?
It's being reacted with more oxygen. And the
Okay,
third
so-
one is opposed to the first.
Okay, so from here to here, does it double, quadruple?
It doubles.
Double. So times 2. So then what happens here?
That doubles.
That doubles, so times 2. So now to find the order of reaction, so I'll do pink for this one. If the rate quadrupled when the concentration doubled, then the order of reaction will be 2 for nitrogen monoxide. Then for oxygen, if the rate doubled when the concentration doubled, the overall order for oxygen will be, or the order with respect to oxygen will be 1. So, everyone with us there? Okay. How to use your chart. So then, we'll plug in what we know. So we know rate is K times the concentration of nitrogen monoxide raised to the second power times the concentration of oxygen to the first power. Alright, so now how am I going to figure out the rate constant? Well, I can plug in because I have 3 scenarios where I know rate, I know the 2 concentrations. Now I know the exponents, so I can solve for K. Now, Liam, which one didn't work?
I think it's the second one.
Second line. You can pick any line. Pick line 1, line 2, line 3. Should work fine for all of them. Whatever you pick is fine. If you pick the first one, I won't have to do extra work when I grade your test. Because I usually don't do the other ones.
There's a blue spot on you.
Yeesh. I spilled acid on myself. Let's hope my skirt lasts for the rest of the day and I don't
I think I was there.
wardrobe malfunction.
I think I was there at the beginning, like before
Was
we
it?
did the experiment. Yeah. I
Wonderful.
should have told you outside.
I don't care about this spot, but I really want there to still be fabric at the end of the day. I don't want to wear my coat for physical science. But I will if I have to. Science must press on, I guess. That has happened to me, but not while I'm teaching. Although I did get to dunk my head and lose some eyebrows because of acid once. So rate, we're going to plug in. We're going to use line 2 because, you know. So the rate in line 2 is 0.112 molarity per second. We're solving for K. Concentration of nitrogen monoxide, 0.250. My unit here is molar. Raised to the second power. Oxygen is okay. So now we've got this whole complicated thing that we're going to plug into our calculator and solve. So